Now in the next problem, for a periodic signal x of n, which is equal to sine of 4 pi over 21 n plus cosine of 10 pi over 21 n plus 1, where n goes from 0, 1, 2 to n minus 1, and n being the period of the signal, we are to determine the magnitude and phase spectrum along with the power spectrum, otherwise known as the power density spectrum. Hope you have understood the problem. Quite similar to the previous one. We have to find the magnitude spectrum, the phase spectrum, and the power density spectrum of the signal. Now let's go to the solution. Here in this case, x of n, if you look closely, x of n consists of numerous sinusoids, more than one sinusoid, one sine function, one cosine function, and one DC value. Let us not consider the DC value for the time being. So, in a signal with more than one sinusoid, in order to determine the fundamental period, in order to determine the fundamental period, omega naught, what we need to do is take the Gcd, which is the greatest common divisor, or otherwise known as the HCF, the highest common factor of both the period. I mean both the frequencies. So in our case, omega naught will be equal to the GCD of this value and this value. So omega naught is the GCD of 4 pi over 21 by 10 pi over 21, which is simply equal to twice pi over 21. Now the question arises, how do I calculate the GCD of two terms? Simply speaking, in simple terms, what you can do is take the highest factor, or take any factor, say from 1 through 10, in this case the highest value being 10 pi. So you divide both the quantities with this number. For 1 it will be pi over 21, or twice pi over 21, thrice pi over 21, and so on, so up to 10 pi over 21. So in order to get the GCD will be the value where both the number can be divided. We need to determine the value for which both the terms get divided with a remainder of 0. That means if we divide both the terms with twice pi over 21, we get the remainder 0. But if we divide both the terms with pi over 21, we can also get the remainder to be 0. But in case of GCD, we must take the highest factor, by which if these two numbers are divided, the remainder becomes 0, in our case, which is twice pi over 21. So twice pi over 21 is the fundamental period. And from this, we know that omega naught equals to twice pi over 21, which is written in the form of twice pi over n, and consequently n in our case is 21 samples. That means the signal will repeat itself after the 21st sample, or if we take from 0 the 20th sample. Now then, coming back to the equation, x of n equals to sine of 4 pi over 21 n plus cosine of 10 pi over 21 n plus 1. These two terms can be expanded using the Euler's relation as such: e to the power j 4 pi over 21 n minus e to the power minus j 4 pi over 21 n over twice j. Plus, for this cosine term, we get e to the power j 10 pi over 21 times n plus e to the power minus j 10 pi over 21 times n over 2, and the 1 remains as it is. So expanding it a bit further, what we get is 1 over twice j e to the power j, let us write 4 pi over 21 like this, 2 into twice pi over 21 times n. That means we are trying to make this term similar or analogous to the synthesis equation. So in the synthesis equation, x of n equals summation of n goes from 0 to n minus 1 c of k e to the power not minus j twice pi over n k. This twice pi over n is omega naught. So j will remain as it is, j twice pi over n, twice pi over 21 is the fundamental period, n remain as it is, and the value of k in this case is 2. So this term becomes analogous to the synthesis equation. For the next value, this becomes negative of 1 over twice j e to the power j of minus 2 twice pi over 21 n. Similarly, for the third expression, we get half of e to the power 10 can be written as j into 5 times twice pi over 21 times n plus half of e to the power j of minus 5 twice pi over 21 times n. Now what about this 1? This 1 can be written as 1 into e to the power j twice pi over 21 n times 0. So if 0 is multiplied over e with this term, this whole term becomes 0 and e to the power 0 becomes 1, and 1 times 1 will give us 1. I hope you understand how we have expanded this equation, this form, into the synthesis equation. And what about the summation? This value, say let us give this plus and a negative sign here, when summed individually we get the summation sign. So one might ask, we have found the value of one who are perceptive has got it by now, that this is the value of k of 2, k of negative 2, k equal 5, negative 5, and k equals 0. What about k equals 1 or k equals 3? There is no value given over here. For that case, the value of c of k is 0. So if there is no term that is k equals 1 or k equals 3 or k equals 4, the value of c of k in that case is 0. So all we need to work is with the value that has a legitimate outcome. Now, upon comparing it with the synthesis equation, we can easily write c of 2 to be equal to 1 over 2j. This is this value for the value of k equals to 2. Similarly, c of negative 2 equal to minus 1 over twice j, that is this value when k equals negative of 2. And consequently, c of 5 to be equal to 1 over 2 c of negative 5, which is equal to 1 over 2 as well, and c of 0, that is this value where k equals 0 to be equal to 1. So these are our required discrete time Fourier series coefficients. Now from this value, what we need to do is that we need to determine the magnitude and the phase spectrum. Now then, previously we got c of 2 to be equal to 1 over twice j, c of minus 2 to be equal to minus 1 over twice j, c of 5 to be equal to 1 half, c of negative 5 to be equal to half, and c of 0 to be equal to 1. So c of 2 can be written 1 over twice j equal to, multiplying the numerator and denominator with j, this becomes j squared, and consequently it becomes minus j over 2, which can be written as 0 minus 0.5j, which can also be written as 0 minus 0.5j. So this is the real part and this is the imaginary part. So in order to determine the magnitude spectrum, we must first of all determine the magnitude of c of 2, which is equal to root over the real part squared times the imaginary part squared whole root. So the real part is 0 plus imaginary part is 0 negative of 0.5 squared, which is equal to 1 by 2. And for the phase spectrum, we get the argument of C of 2 written like this equal to tan inverse minus 1 by 2 over 0, which is tan inverse the imaginary part by the real part, which is equal to tan inverse negative infinity, which is equal to minus pi by 2. Now similarly, for C of minus 2 we get 1 over minus twice j, and multiplying the numerator and denominator by j, we get this to be equal to minus 2j squared, and this in terms become j over 2. Obviously j squared equals minus 1, we all know that, and this in turn becomes 0 plus 1/2 of j, and consequently the C of minus 2, the modulus or magnitude becomes root over 0 squared plus half squared is equal to 1/2. Now, determining the argument or the angle, C of negative 2 is equal to tan inverse the imaginary part over the real part, tan inverse 1/2 over 0, which is tan inverse infinity, which equals pi by 2. Now similarly, for we have done for this value, now let us go to C5, which is 1/2, can be written as 1/2 plus 0 of j. From here we can get the magnitude C5 to be equal to root over half squared plus 0 squared is equal to half, and the angle C5 equal to tan inverse the imaginary part being 0 and the real part being 0.5, so tan inverse 0 equals 0. Similarly, for C of minus 5 we get the value half of C of minus 5 also yield the value of half plus 0j, and the magnitude C5 equals root over half squared plus 0 squared to be equal to half, angle of C of negative 5 to be equals to, this is negative 5 to be equal to tan inverse 0 over 0.5 tan inverse 0, which equals 0. Now the last term, which is C of 0 equal to 1, can be written similarly as 1 plus 0j. So as you have seen, C of 0 magnitude will become 1 squared plus 0 squared equal to 1, and the angle for the phase spectrum C of 0 becomes tan inverse the imaginary part, which is 0, over the real part 1, which is 0. So now if we plot the magnitude and the phase spectrum, here we first plot the magnitude spectrum C of k. So at point k equals to 0, when k is 0, magnitude of C of k is 1. And when k is 2, for this value, the magnitude is half. Similarly, for k of c of negative 2, when k is negative 2, the value is also half. Again, for C5, when k equals 5, the value is half. This is 1, 2, 3, 4, 5. This is half. And in the negative side as well, C of minus 5. So 1, 2, 3, 4, 5. This part is also half. So ladies and gentlemen, this is the required magnitude spectrum. For the phase spectrum, we get angle of C of k in the x-axis. When c equals 0, k equals 0, the angle is 0, so at 0 it is 0. At c of 2, so 1, 2, it is negative pi by 2, so negative pi by 2. At negative 2, it is positive pi by 2, so 1, 2. At negative 2, it is positive pi by 2. 3, 4, 5. At positive 5, it is equal to 0. 1, 2, 3, 4, 5. At negative 5, which is this value, it is also equal to 0. So this is the required phase spectrum. Now, if we want to determine the power spectrum, simply we need to do is square this term. These terms will become squared. Here it will be 1 over 4. This will be 1 over 4. This will be 1 over 4. And this will be 1 over 4. So, in the blue marked position, we get this to be, and this will remain 1, because 1 squared is 1. We get the power spectrum or the power density spectrum. So ladies and gentlemen, I hope you are able to understand the problem and determine the magnitude and the phase spectrum of any signal along with the power density spectrum. With that, let's move on to the next part and solve another problem of this type.